All right. Well, hello, everyone, and welcome to the 2026 Statistically Speaking webinar series, which is brought to you by the Data Science and Analytics for Precision Rehabilitation Center and the Repro Rehab Training Program, both of which are funded by the Eunice Kennedy Shriver Institute for Child Health and Human Development. This year, the focus of our webinar series is to equip rehabilitation researchers with principled and phase-appropriate approaches to sample size planning, from feasibility and pilot studies through, clinical trials and effectiveness research. My name is Keith Lose, and I'm the moderator for the webinar. Our guest today is going to be Dr. Kristen Sinani. And before I introduce Dr. Sinani, I want to remind everyone to please mute your microphones for the first part of the session during Kristen's talk. In the event someone is unmuted, please don't be offended if me or one of the hosts puts you on mute. The first part of the webinar will be a presentation from Dr. Sinani, and if you have clarifying questions during that time, please put them in the chat, and then I can ask them as the moderator. As a reminder, the initial part will be recorded and later posted to the Repro Rehab YouTube channel. After Dr. Sinani's presentation, we're going to stop the recording to open the floor to a Q&A. Kristen has a point where she may have to dash off and then jump back on in that transition. So I will do my best to tackle any questions in that time and buy Kristen a few minutes in between the end of her presentation and the Q&A. But without further ado, it gives me a lot of pleasure to introduce Dr. Kristen Sinani, who's a statistician and professor of epidemiology and population health at Stanford University. I'm really excited to have Kristen talking to us today because not only I think is Chris is a great statistician, but she's a fantastically clear writer and presenter. In fact, she has a Coursera course on scientific writing that I would encourage you to check out if you're not familiar with it. And she is also a podcast host, which I think she may mention in her own slides. But if you're looking for a really fun diversion into sort of scientific research methods, made more palatable by lots of really amusing stories, I'd strongly encourage you to listen to her podcast with co-host Regina Nuzzo called Normal Curves. It's a lot of fun. And with that, I will mute my mic and turn it over to Kristen.
Thanks, Keith. Thanks for inviting me to come speak. And as Keith mentioned, I'm going to be modeling good work-life balance today. So I do have to run off for a few minutes in between the talk and the Q&A to drive my daughter somewhere. She has an appointment. But I will be back on and Keith can handle the questions for a few minutes while I have to do that. But again, work-life balance, really important. So I'm going to model that today. So I've been asked to talk about aligning your study design with the hypothesis of interest. So that's going to be the subject for today. As Keith mentioned, I do have a podcast, which if you want to learn about statistics in, again, a way that it's a lot of stories and a lot of making it really fun. And then there's we drop in some statistics training. I was saying to Keith that when I got on today that I almost feel like, my lectures now seem so boring in comparison because I'm just talking about statistics and there's no, jokes and stories thrown in. We have a really fun episode that's coming out on Monday about marathon fueling. So check it out, Normal Curves. For today, I thought we'd take 3 steps back and just mention the difference between exploratory and confirmatory research because everything I'm talking about today presumes that you have a hypothesis that you want to test. And we, of course, want to be doing hypothesis-driven research, but there is nothing wrong with doing exploratory research if that is the goal and you're transparent about it. And so I just want to remind people that it's perfectly fine to do exploratory research, but you need to label it as such. And I think of exploratory research a little bit like beachcombing. You are looking around the beach for anything exciting, fun shell, sea glass, and that is totally fine. But it's very different than confirmatory research, which is much more like, hey, I am going to the beach to find my lost sunglasses, and I know what I'm looking for. I can describe it. I can know when I found it or not. Again, nothing wrong with exploratory research, but don't disguise it as confirmatory. So if you find sunglasses while beachcombing, don't pretend that you were looking for them all along. And there was a lovely paper out in the Journal of Sports Sciences recently about exploratory research, which I recommend people read. If you want to do exploratory research, again, perfectly fine, but not exactly what I'm talking about today. For confirmatory research, we need a primary research question. And I work with a lot of students, and this is so common that students come to me, how am I going to analyze my data? And we have to go three steps back, and I have to say, okay, so what was your research question? And a lot of times they don't have that well thought out. You need your research question well thought out before you design the study. I had a student come to me yesterday, hey, I'm doing a clustering analysis. And I was like, great. What's the research question? And he didn't know. So we had to go three steps back and say, let's start at point one. It's not just I have data and I'm going to do something with it. We start with what's the research question. So it's the most important thing. You need to get that right. And I think this entire series, Keith, probably sounds like it's a lot of figuring out your research question and how to plan your study well. Um, it does mean that sometimes you can't look at everything that you're interested in. It has to be very narrow. And that research question defines how you calculate sample size and, of course, the limits of what you can conclude at the end of the day. And so there's, can't say it enough that the primary research question is paramount. I'm going to talk about a specific part of the research question today, but I wanted to just remind everybody about PCOT. So when you have a research question, right, you need to define the population, you need to define the intervention, you need to define the comparison, and I think a lot of times the comparison, that's where sometimes people don't think carefully about what is it I'm comparing to. Um, the outcome needs to be clearly defined, and you need a specific primary outcome. And this is where I see probably most of the problems, or a lot of the problems in sports science research, where people say, hey, I'm going to look at performance outcomes. Well, what is that? Right? And that can be 20 different things. And then you run into a type 1 error problem. So when you're designing a study, you have to designate one of those outcomes as primary. And I see in most or a lot of the research that I review for sports medicine and sports science, often they're missing having designated that primary research question. So, this series is about sample size. The typical sample size calculation, if they have one, I see is like, we powered this for a Cohen's d of 0.8. So I'm like, 0.8 for what? What variable are we talking about? So cardiovascular outcomes, performance outcomes, training outcomes, too vague. Reduction in LDL, we need a specific. And of course, we always want to talk about the timing of the study. So a research question should look something like, in the specific target population, does this intervention compared to this comparison result in better, no worse, or equivalent for a specific outcome at a certain time? And what we're really focusing on today, though, is this better, no worse equivalent, right? What is it I'm trying to show? Am I trying to show that two groups are the same? Or am I trying to show that two groups are different, that one is not worse than the other? That has to be worked out ahead of time because it completely determines your sample size calculations. So research question, I'm going to use marathoning as example today. This is not a good research question, right? The research objective was to determine whether a marathon training app improves training outcomes. Too vague. So who are we talking about? What's the population? I'm guessing marathon runners, but I don't know because you haven't specified. There's some kind of marathon training app. What are we comparing to? Improves compared to what, right? Training outcomes. We see this too often in sports science, performance outcomes. What do we mean by that? What's the primary outcome? And what's the time frame? So a better research question would be something like, among first-time marathon runners aged 18 to 65, does the use of a marathon training app increase average weekly mileage compared with a standard paper training plan over a 16-week training cycle? I don't know if anybody uses like the old-fashioned, I still have like an old-fashioned logbook where I write down my running, but we want to see, does the app actually, if you get complicated with your Garmin online, does that help you? The outcome being the average weekly mileage. And we want to know if the app is better. So this is a superiority study, right? We want to know if the app is better than the old-fashioned, just write it on a piece of paper. We start with the research question, and then we have to take that research question and we have to turn it into a statistical hypothesis, right? And they're not the same. The research question is the broad knowledge gained from the trial. The statistical hypotheses is a set of formal mathematical statements, and I like to actually write down the actual mathematical statement. And I like it when people write that in their paper. You don't have to use the mathematical symbols, but you need to say in mathematical terms what is the null hypothesis? What is the alternative hypothesis? So everybody is familiar with null versus alternative. I like it when in a paper they actually state those. Sometimes it's obvious and maybe you don't need to state them, but like when I see that, then I know that you've thought specifically about exactly what flavor of hypothesis testing you're doing. And we're going to talk about a lot of different flavors of hypothesis testing today. So just as a reminder, the null hypothesis, it's a weird way of thinking, right? That's the thing that we are trying to like the straw man we are trying to take out, like the punching bag. We are trying to knock that down. And it's very confusing, I think, for students because it's sort of the opposite of what you want to prove. But why do we have to do that? Because in science, we can't really prove that something is equal or something is different. We can only disprove things. So what we're trying to do is we're setting up this straw man that we can then disprove, and we're left with the alternative hypothesis. And so the most important thing when you're setting up your sample size calculation and planning your study is you have to know very clearly what is my null and what is my alternative. And again, I think writing it down in mathematical terms is really the best way to get there. So if we have this new marathon training app and the goal of our study is to say, hey, we want to show, we're hoping to show that it increases mileage in these first-time marathon runners compared with the old-fashioned way. What is our null hypothesis? What is our alternative? Well, in this case, we're trying to knock down that it does nothing, right? So we start with the null hypothesis that, hey, it's no better. The training app is no better, no worse. It's about the same as the old-fashioned paper training log. And so the null hypothesis is it has no effect on mileage, right? So we start with what we want to disprove so that we can then accept the alternative hypothesis, what's left standing. So once we knock down the null hypothesis, what is left standing? That's our alternative hypothesis. And usually that's the thing we're hoping to show, right? And so in this case, if our null is that the new app has no effect on mileage, the alternative is that the app changes mileage. Now we want to show that it increases, but if we're working in our traditional null hypothesis significance testing framework, we usually make it two-sided, meaning we're open to, hey, it could actually be worse. So our alternative is typically for null hypothesis significance testing, just that the effect is not equal to zero, that there's some difference between the groups, whether it's positive or negative. So that's the most common hypothesis testing framework that we see in most of the literature. I'd say the majority of papers, right? You see null hypothesis significance testing. That is ingrained in the literature, and it answers one very narrow question, which is just, is the effect different from zero? The null is usually the effect is equal to zero, or whatever the equivalent, if we're talking an odds ratio, the effect might be 1.0, but whatever the equivalent is of no difference between the groups. And the alternative is just saying it's not equal to zero. So in this case, in our example about the mileage and the marathon app, we don't usually say this when we're stating our research question, but kind of hidden, implicit in our research question is we're hoping to show that we can increase mileage by any amount. In other words, anything other than zero. We don't say that, but that's really what we mean when we're doing null hypothesis significance testing. We'll take any difference from zero. So it doesn't matter if it's a lot or small. It's just zero or not. And we can kind of put it in a nice little picture. So our null hypothesis for null hypothesis significance testing is this 1.0, right? The difference between in the average weekly mileage between the app versus the paper plan, that difference is equal to zero, meaning that the two groups are equal in their average weekly mileage. That is our null hypothesis that we want to shoot down. It's 1 point. We are, of course, hoping to show that the app is better, right? That we end up in this positive range above zero, that the app does better than the old-fashioned paper training plan. We, as I mentioned before, we are open to discovering that the app is worse. Personally, I'm not really sure. You know, I'm old-fashioned. I ran like 30 years ago. So we wrote everything on a piece of paper. I don't know that the app is better. I know there was something nice about the old piece of paper, right? So my coach used to send me in the mail, you know, I'd get a monthly schedule on the old-fashioned paper. I still have those. Something nice about that. So maybe the app is worse. Like maybe it's not actually great having all of this amount of huge deluge of information about your runs, and the old-fashioned way might be better. We call that a two-sided hypothesis test, because we are open to the fact that actually the app could be worse, right? I do believe that that's a possibility. So our alternatives are that the mileage with the new app is not equal. It's not exactly equal to the paper plan, and it could go either direction. That's the two-sided nature. One possible result you can imagine, let's say we do a study and we get a 95% confidence interval for the difference in that average mileage app minus paper plan, meaning positive means the app is better, and our whole 95% confidence interval is above zero. Then we get to conclude, we get to reject the null hypothesis that that difference is zero, and we get to conclude that the app is superior to the paper plan. That's our very typical, what you see in most papers, null hypothesis significance testing. If the confidence interval crosses zero, we really don't get to conclude anything. We just get to say we haven't shown that it's superior. And that's very unsatisfying to people. So that leads us to the discussion of that the world is bigger than null hypothesis significance testing. I think, it's just become the most common way that people design studies because it's habit and that's what journals expect. And so you don't see a lot of variations from this, but there are a lot of other choices that you have when designing a study, and you need to make sure that your scientific question that you actually want to ask, that aligns with the framework you're using. So instead of just asking, is there any effect, which is what null hypothesis significance testing asks, we could ask, is the effect big enough to matter? So that's what we call minimal effects testing, right? Not just is it different than zero, but is it bigger than an amount that we believe is, big enough to be practically significant. We could also do something called non-inferiority testing, which probably a lot of you have seen in the context of clinical trials. So is some new option that we have not worse than an old option? So we're not trying to show it's better. It's just we have an option that's good, and maybe our new option is cheaper or easier to use. So we're just happy if it's not worse than the old option. Sometimes we're trying to show that two things are equivalent. And by equivalent, we can never show that they're exactly equivalent, but sort of equivalent within a margin too small to care about. And then sometimes we don't care about hypothesis testing at all. So we want to throw in that sometimes we just want to estimate, right? Just how big is the effect? And there's actually not, the goal may not be to test against a particular number. We just want to say we want to estimate the effect. All of these require us to define something called the smallest effect size of interest. And Keith makes these wonderful cartoons that he shares on LinkedIn. I did this in ChatGPT, so it's not as good as yours, Keith, but I thought it was kind of cute. We can put all of this together kind of in a nice, I like to have little tables, or you can refer to what are all what's the progression here. So we take our scientific question, is there an effect or not? That's null hypothesis significance testing. Is the effect big enough to matter? That's minimal effects testing. And then we start to try to put this in mathematical terms where we write out those null and alternative hypotheses. So I'm going to kind of go through each one of these, starting with minimal effects testing. The goal with minimal effects testing is to say, not just is the effect different than zero, but is it big enough to matter? So what we're trying to show is that the effect is at least as big as some minimal, smallest effect size of interest that we think is big enough to care about. For this marathon training example that I'm using, I'm going to say that's 3 miles per week. That is completely arbitrary and made up out of thin air. Usually we want to put some thought into the smallest effect size of interest, but since this is a made up example, I'm just going to say if you run 3 more miles per week, that's enough to care about. So minimal effects testing is, again, the scientific question, is there any meaningful effect? And what's really important is the null hypothesis and the alternative hypothesis. Minimal effects testing is often set up as a one-sided test. The null hypothesis is just that the effect is too small to care about, which could include that it's worse than that the app is worse than the paper training plan, but it's just, or it can include that it's better, but by too small an amount to care about. The alternative is that the effect is at least as big as that smallest size of interest that we care about. So we're trying to show that we're increasing mileage now, not just by any amount, but by a meaningful amount. And we can draw a little picture. I like to show it visually. Our null hypothesis now is that we are either below the smallest effect size of interest here, 3 miles per week. We can be below that, but above zero, or we can be below zero. So anything that is lower than 3, if we are not improving by at least 3 miles per week, it's not worth changing to the app. You maybe have to pay money for the app, right? You might as well stick with the paper plan. So that's our null hypothesis that we're trying to shoot down. That the app is not meaningfully better, which includes small positive values, but that are too small to care about. What we're hoping to show is that that the app does better than this 3 miles per week. Again, the 3 miles per week is arbitrary, but let's say we actually put some thought, and that seems to be, a good amount, that enough to care about if you could increase your weekly mileage by 3 miles per week. For me, that's probably 3 miles per week increase is doing pretty good these days. So our alternative hypothesis here is that the average mileage with the new app is at least 3 miles per week better than the old training plan. One-sided hypothesis, because we only care if it's better. Anything on the other side, that's all of our null. And what we're hoping to be able to conclude is that the app is meaningfully better. You can do minimal effects testing on both sides, two-sided, but we typically would do it as a one-sided test, because if it's less than 3, I don't care whether it's worse. I just care that it's less than 3, not good enough for me to switch over to the new app. So if we got a 95% confidence interval that's completely above 3 miles per week, we get to conclude that the app now is not only superior to the paper plan, but meaningfully superior to the paper plan. Now, obviously, this is a stronger conclusion, right, than we would get from null hypothesis significance testing. Why don't we always do it this way? Well, it requires more a larger sample size, because now you have to distinguish not just from 0, but from 3. So your sample size requirements might be higher. So we don't see this as often in the literature, but arguably this would be a good way to do this, because now you can say it's meaningfully superior.
And Kristen, can I actually
Yeah,
interrupt you there
yeah,
to ask
please.
a question from the
Yes.
chat? Kind of how do we establish that smallest effect size of interest, and how
Yes.
how is meaningfulness defined?
Oh, that is a great question, and we can get into a lot of philosophical discussion. 3 miles per week is totally made up by me for this lecture with no thought other than random. Yeah, normally we would want to put some thought into it. So there's different ways that people come up with that. They may anchor it to something like the standard deviation of the measurement, right? It's a certain number of fraction of a standard deviation could be called meaningful, or some actual clinical knowledge. And I kind of prefer the clinical knowledge, right? Like, I know enough about marathon training that I might have some sense of, hey, what is going to actually translate to a change in performance? How would I know that through other research that's looking at the relationship between this outcome and performance, right? So it should be something that you actually put a lot of thought into. And there's a number of different approaches to defining that. And yeah, so it shouldn't be something you make up out of thin air. I like to anchor it. I think the clinical anchoring in some ways is better than the statistical anchoring, that a certain amount of this has to do with clinical judgment, that which is where the non-statisticians are very important.
Perfect. Yeah, because I think that comes up a lot where probably the most commonly reported ones are those like Cohen's d, oh, we think like zero point 0.5 standard deviations, right?
Right.
But
Yes,
that's
yes.
probably the worst case scenario. And
Right.
ideally you have something else.
I'm not a fan of those. I'm not saying that, if you had no knowledge clinically, well, maybe you wouldn't even be ready to be doing this kind of testing. There might be a case where you could make a case for defining it based on something like that. Sometimes for non-inferiority trials, they're basing it on half of the size of the effect, right? So there are these kinds of rules of thumbs that people have come up with. But I like the idea of clinical judgment coming in. Right.
Perfect. Thank you.
Yeah. And yeah, and just to be clear, the 3 is totally made up. All right, so minimal effects testing is one option. Non-inferiority trials, we do see more in the literature than we see some of these other options, I think, because it's often used in the context of clinical trials. Pharmaceutical companies heavily use non-inferiority testing because what you're often trying to do with the next big blockbuster drug is not necessarily to lower cholesterol more or lower blood pressure more, or treat, HIV better, but to come up with a treatment that is not meaningfully worse than the old treatment, but is somehow more convenient or cheaper. Often convenience factors in, right? You only have to take 1 pill a day rather than 2 pills. So there is This is very common if you're in the drug literature, I think. I don't think we see it as often in sports science and medicine just because we don't deal with pharmaceuticals typically. There may be some cases of treating different injuries. Is the uh, ultrasound shock waves not worse than whatever the way we treat injuries is? So in this case, we are trying to just show that the new methods, there's something new, some new treatment, is not meaningfully worse than the old treatment. So the null hypothesis here would be something like the effect is less than or equal to that minimal, but on the negative side. So if we're using our marathon example, that my app is not more than 3 miles per week worse, negative 3 miles, a decrease in mileage, no more than 3 miles per week. And again, this is a one-sided test, so our null is just anything less than that smallest size negative version of the smallest size of interest, and our alternative, if we shoot that down, is that the effect is bigger than that. So that would include cases where you might have a negative effect. It's a little bit worse, but it's not worse enough to care about. So I made up kind of a new example for this one. So let's say we are comparing, we've got this new app for marathon training, and we want to sell this app. So we want to say, hey, this is, not worse than a personal coach. So we're not trying to prove that an app is probably never going to beat a personal coach, but we're going to say, hey, if you buy this app rather than paying a personal coach, it's at least you're not going to do any worse than you would with a personal coach, right? Maybe we get some AI in this app and the AI coaching, not worse than an actual human. So our setup for this, our null hypothesis is again an entire range, but now instead of being lower than the positive smallest effect size of interest, we just need to be lower than the null is just lower than the negative version of that. So the null hypothesis here would be that our app compared to the personal coaching, we're not doing worse than a 3 mile per week loss decrease in mileage per week. If we are able to reject that, we get to conclude that the average mileage with the app is not meaningfully worse. It might be a little worse, but it's not meaningfully worse than with the personal coach. And that's what we're really hoping to show. Because then again, maybe for marketing, we can say, look, our app is much cheaper than a personal coach, but it's easier, it's faster, and it doesn't do much worse. And so, hey, I think we're going to get a lot of this non-inferiority now with AI. Is AI not meaningfully worse than a human being, right? So that could be the context here. Maybe there's some AI built into our app. Maybe it does a pretty good. So you can imagine getting a result that looks like this. So here's the 95% confidence interval. And this one's interesting, right? If you look at the 95% confidence interval, this is a potential result that you might see. If we were doing null hypothesis significance testing here, notice that the 95% confidence interval falls below 0. So that means that actually, technically, the personal coaching was superior to the app, or in other words, the app was inferior, significantly inferior to the personal coaching. It does a little bit worse. But because we can show that, in fact, the confidence interval is the lower bound of the confidence interval is above negative 3 miles per week, we can say, well, yeah, it's a little worse technically, but it's too small to care about. Loss of 2.5 miles per week of mileage, not enough to care about. So you can get away with using the app, and it's not a meaningful loss in your training outcomes, right? So that's the idea with non-inferiority, but it's interesting, I think, that you can be non-inferior and inferior at the same time. Like technically, this is significantly inferior, meaning by any amount, but it's not inferior, right? Because the amount is considered too small to care about. The last kind of flavor of hypothesis testing that, again, we don't see as often in the literature as we might like to, because I think sometimes this is what people are trying to do. They're trying to prove equivalence, but they don't know it. And we get into, I'll show an example in a minute, this idea of like, hey, I want to show things are equivalent, and I'm going to say that the p-value is not significant. And that doesn't tell us that they're equivalent. In order to show equivalence, we have to flip our null hypothesis to make it, the null hypothesis is that there's an effect, a meaningful effect, and the alternative is that there's no meaningful effect. So if we want to show that two things are equivalent being we can't ever show they're exactly equivalent, but equivalent within a certain margin, what we're really trying to show is that the effect is lower, smaller than the smallest effect size of interest. We call this equivalence testing or two one-sided tests, toast, because as you'll see, the null hypothesis actually has two one-sided tests embedded in it. So again, the scientific question here is any effect small enough to ignore? Any difference between the groups? Maybe it's just small enough to ignore, and we can say that these two treatments, these two interventions are effectively equivalent. Our null hypothesis then has two one-sided parts to it. So one of the null hypotheses is that the effect is lower than that minimal effect size of interest in the negative side, meaning we're meaningfully worse. Like the app is meaningfully worse um, than the coach. And the other null hypothesis is that the app is meaningfully better. So we're starting by assuming that there is an effect, and we're trying to prove that there is no effect, right? So the alternative would be that there is only an effect that is so small that we don't care about. Um, just to give a new example on this one might be something like when would we be trying to show equivalence? So maybe we've got an app that works really well and it's developed for the Apple iPhone, but now we've made a new app that's for the Android. And we want to show, hey, the Android app is just as good as the Apple app. We don't need to show it's better. We're not trying to show non-inferiority. We're just trying to kind of say, hey, they're kind of the same. They're comparable. In statistics, we can never prove that something is exactly equal. So we just want to show equal within a, kind of margin of error. So again, looking at the picture, our null here is that we are in the meaningful effect size ranges. We're starting by saying, hey, let's assume that those are different in either direction. That's your two one-sided tests because we have to do each direction separately. What if we reject those? What are we left with? The alternative, what we're trying to show, is that there's no meaningful difference between the old app on the iPhone and the new app on the Android. So that there's any difference, of course, there's never gonna be perfectly zero, but it's all something there's no meaningful difference. So we're trying to get the entire confidence interval in that equivalence range. So if we come out with a 95% confidence interval where the result is what you see here, it's entirely between -3 to +3 miles per week. That's our smallest effect size of interest here. Then we can say, hey, they're effectively equivalent. We can never say they're perfectly equivalent, but they are effectively equivalent. And sometimes that's the goal, right? Is just to show that two things are the same. But obviously, you have to design the study going in. You can't decide at the end of the day, hey, I'm doing null hypothesis significance testing, and then at the end of the day you don't find anything, and then you declare I've done an equivalence test, right? That everything has to be set out ahead of time. You have to set out what that equivalence range is ahead of time. You don't get to decide it afterwards, right? So the last type of different framework that we can think of that's important for, again, our sample size determination, sometimes we're not after a hypothesis test at all. Sometimes we're just trying to say how big is an effect. Probably one of the most common places this comes up is in reliability testing, right? If I want to know that my measurement is reliable, I don't necessarily care that it's different than zero, right? I want to know is it 80% reliable? Is it, 70%? So I really care about the estimation and not comparing to a certain bound. In this case, maybe we don't have a specific hypothesis we're testing. We just want to say how much the app differs from the paper training plan, and we are just setting out to build a confidence interval and a point estimate and describe the size and direction of the effect. And sometimes that's all we're setting out to do, and we're not actually doing hypothesis testing. Your power calculations, of course, are completely different if you are trying to basically make sure that you come out with a narrow enough confidence interval at the end of the day. Again, I think the most common place this comes up would be something like reliability testing, where you're trying to say what is the reliability, not that it's different than zero, because different than zero on reliability doesn't really tell you much. So we can kind of put these all together in a little schematic. So if we are between the bounds of our negative, smallest effective size of interest and positive, we can call that equivalent if the entire 95% confidence interval is in those bounds. If we're above the negative bound, we can call that non-inferior. If we are above zero, but not necessarily a meaningfully amount, we get to call it superior, different than zero, but not necessarily meaningfully. Same in the other direction if we're negative, but not above any certain bound, we get to call that inferior. If we want to say something is meaningfully superior, we have to set that upper bound, that's smallest effect size of interest, and show that the entire confidence interval is outside of that range. And similarly, if we wanted to talk about meaningfully inferior, it has to be below that negative bound, right? And of course, you can get lots of other results where the confidence intervals cross some of these, and then often we end up with something that's inconclusive where we can't really make any, we didn't manage to prove what we were set out to prove.
And actually, Chris, that
Yep.
relates, I think, to a question in the chat about
Yeah, great.
essentially like, what constitutes like a failed result, or how do
Yes.
you how would you talk about those inconclusive results maybe
Right.
across these different
Inconclusive results
scenarios?
are verbally terrible, right? So because we have to say we didn't prove that it's, you know, meaningfully superior. You don't get to say it's not meaningfully superior. You just get to say we didn't prove that it's meaningfully superior. And that distinction matters. And I'm a clear language person. And this is one of the places where I feel like there's no clear language way to say it that's accurate, right? So you have to have knots in there. So for example, let's say you were doing an equivalent study and this equivalent, this 95% confidence interval extended past the positive smallest effect size of interest extended out here. What do we get to conclude? We say we don't have proof that it's equivalent. We don't get to say it's not equivalent. We have to say we don't have evidence that it's equivalent. I hate that verbally, like in my clear language, mission in the world. It's the one place where I think you actually have to be very precise and put a not in. Same with like, what if this non-inferiority, if it extended past the negative smallest effect size of interest, we get to say, well, I haven't proven that it's not inferior. I don't get to say it's
Right.
inferior. I just haven't proven that it's not inferior, right? Now, I will say that sometimes if you set out to do if you set out to do a non-inferiority test, for example, but your confidence interval came out in the meaningfully superior range, you can make that conclusion. So you can tack on extra conclusions. You're not increasing your type 1 error in a planned study. If you planned it to be non-inferiority, but you come out meaningfully superior, you do get to make those claims. But when you're crossing all the bounds, you basically get to say, I did not reject the null.
Yeah.
And there is so you could say it's non-inferior and it's meaningfully superior if both of those are true. But if you're crossing bounds that mean you don't reject the null hypothesis, you basically get to say, I didn't reject the null hypothesis. I don't know, Keith, have you ever found a better way of like putting that into
Yeah.
words?
It's cumbersome. I think like the analogy that's graspable, maybe because I've
Yep.
watched a lot of Law and Order over my life, is like
Oh, I like
like
it. Yeah.
it's like innocent until proven guilty, right? It's like null
Yes.
until proven otherwise. Right.
Yeah,
And
exactly.
and
Yes.
so the exactly what the null is changing in each of these situations. But it's like, well, okay, I didn't prove that it's superior, and therefore it's not superior,
Right.
whatever it might be. Yeah.
Right. Yes. Yeah, I like that. I like that analogy actually because you're not saying that the person is innocent,
Right.
right?
Yeah.
You're saying that, innocent until proven guilty, but we're not concluding that they're innocent. It's just that we haven't proven them to be guilty, right? I think it's a
Exactly.
good, yeah. That is a very good way to think about it. Yeah. It's in words, sometimes people will say inconclusive. I think that's the kind of the easy way to say, hey, we didn't prove anything. So we get to say inconclusive. And that's the one way to avoid the word not, I think. But
Mm.
we will be very careful. And just because you didn't prove it, right, again, um, if your confidence interval extends you did an equivalency test and you extend past the positive smallest effect size of interest, you don't get to say they're not equivalent because that would mean they're different. You get to say we haven't proven that they're equivalent, and that distinction really, really matters because not equivalent means something. It means that they're different, and we can't conclude that they're different. We can conclude that we haven't proven that they're equivalent. I mean, it's language wise, not a lot of, but inconclusive might be the easiest way to say it. Yeah.
Yeah.
All right, I want to give two examples of the kinds of things I see in the literature where people have misaligned their study design with the hypothesis of interest, and there's no rescuing it, unfortunately. So these are papers that when I review them, I'm going to say there's nothing you can do now. You cannot fix it after the fact. And this is why this whole discussion about planning is so important because it's too late once you realize that you've done the wrong study design, right? So there was an example I saw a few years back where researchers wanted to show that a topical cream, a topical non-steroidal anti-inflammatory, was no worse than like an oral NSAID, like a ibuprofen, for treating a particular type of joint pain. So we know that the oral NSAID is effective, but it can be hard on the stomach. Some people can't tolerate it, and so it actually would be great if there was a topical NSAID that was at least no worse at relieving pain. So we don't need it to be better. We just need it to be no worse at relieving pain compared with the oral formula. So that they actually even used the terminology non-inferiority study. They kind of knew that that's what they wanted to do, but they designed the trial as a superiority trial, as a null hypothesis significance testing trial. So unfortunately, that means when they got their results, there was nothing they could do with them because this is how they presented their results. They said, hey, we've got our topical group. They started at a pain score of 5.5 and they went down to 3.3. Look, that's a significant improvement. And then our oral group, they started at 5.5 and they went down to 2.9, also a significant improvement. We see in the, in the table, but the between group, when we compare topical to oral directly, those changes, the dropping to 3.3 versus the dropping to 2.9, those changes, oh, look, not significantly different. So they go, okay, they're not significantly different. So the topical treatment is non-inferior to the oral treatment. That's not correct, right? The lack of a significant difference in null hypothesis significance testing. Remember, what did we start with? Our null here is that they are the same. And just because we didn't find a significant difference, that does not mean we've proven that they're the same, right? So this is what we were just talking about. We have not proven that the topical is innocent. We've just proven, all we can say is we didn't conclude that they're different, right? And that's not the same as non-inferiority. So they had the idea in their head of they were trying to do non-inferiority, but they didn't set it up as a non-inferiority trial. The difference that they found was negative zero point 0.4 on a 10-point pain scale that favored the oral NSAID. The 95% confidence interval was negative 1.95 to positive 1.15. So you can look at that and say, well, oh, it crosses zero, so it's not significantly different. But as we all know, no evidence of a difference is not proof of no difference, right? This is a very common statistical fallacy. And it was too late for them to do anything, right? At this point, they did not design it as a non-inferiority. They did not pre-specify. The key to a non-inferiority trial is you have to pre-specify what we could sometimes is called the non-inferiority margin, which that's just the smallest effect size of interest. You have to pre-specify that. If you don't pre-specify it, well, you could just decide it after the fact, and obviously that is not going to, then you're just cherry picking. So if, let's say they had designed it as non-inferiority and they came out with a confidence interval, let's say the smallest effect size of interest was predefined as 1 point less in pain, like we're okay with it as long as the pain with difference in the pain score is only 1 point. They wouldn't have made it. They wouldn't have made non-inferiority because you can see that the confidence interval crosses into that range where the topical cream is meaningfully inferior. They can't, after doing the study, go, oh, well, -2 is our smallest effect size of interest, right? You can imagine somebody doing that is to say, oh, well, we got to confidence interval of negative 1.95. And then after the fact, we decide that we only care if it's 2 points different, right? That would be wrong. Now, they in their favor, they didn't try. I think they didn't understand non-inferiority testing, so they didn't try to pull a spin like that. But obviously, you need to decide ahead of time because you can't just look at the data and then make that call. You have to decide it ahead of time based on all the factors that we talked about before. There has to be a rationale for it. And in this case, it's too late. There was literally nothing they could do because it wasn't a non-inferiority trial. They would have to redo the entire thing. So you don't want to find yourself in that place where you've designed this whole trial, you've run this whole study with this particular question in mind, but you haven't run it right, and now there's nothing that you can conclude. Another example I saw recently, researchers wanting to show ultrasound has good reliability compared with the gold standard of MRI for diagnosing bone stress injuries. And so one of the Cohen's kappas they reported was 0.75, and they said, hey, but it's statistically significant. Great. So here's the problem with that, right? Reliability being statistically different than zero, right? But what that could include that your reliability is 0.02. A reliability of 0.02 of ultrasound compared with MRI means that the ultrasound is not good, right? And so we need to know that the ultrasound is meaningfully reliable, meaning it's a high enough reliability, either Kappa's Cohen's Kappa, sometimes we see ICC. So we need to actually, what we care about really in a reliability study is estimation. We want to estimate the 0.75 and then we want to put the confidence interval. So if the confidence interval is zero point 0.7 to zero point 0.8, we can say, hey, that's like reasonable reliability compared with the MRI. But if the confidence interval is 0.01 to 0.99, it's pretty much useless, which I have seen in papers where the confidence interval for reliability pretty much spans 0 to 1, which means it's absolutely useless. You could also do minimal effects testing here because you can imagine wanting to say, I want to show that the reliability is at least 0.7, right? So you could make a minimal effects test where you're trying to show that the entire confidence interval is above 0.7 because you have some minimal reliability that would make it useful for you to use ultrasound in your clinical context, for example. So either estimation or minimal effects testing is necessary here. Null hypothesis significance testing for reliability is completely useless because we're not trying to show that it's significantly different than 0. That's not enough. That doesn't make it reliable, right? I see this quite a bit with reliability studies. And again, it's too late to rescue it because you need to design your study with enough power that you can have a narrow enough confidence interval to be able to say something other than the reliability is, 0.01 to 0.99, which I've literally seen in papers, which is completely useless, right? So, all of this is to say that you need to know which one of these you're doing, which question you're answering before you do your study so that you can align your sample size planning with your design goal. If you're doing null hypothesis significance testing, you are powering your study to reject a null value of 0. You have to assume some non-zero effect in that power calculation, of course. But that's different than if you're doing minimal effects testing, where then you're powering against a null hypothesis where there's actually a bigger than 0 effect that you're trying to reject. That typically takes a bigger sample size. Non-inferiority trials, you have to set that non-inferiority margin ahead of time. And again, you have to power your study to make sure that your confidence interval is going to be narrow, that it's not falling into that inferiority range. Equivalence testing often takes quite a bit of power because you're in a really narrow confidence interval to have it all within the negative to positive smallest effect sizes of interest. And if you don't plan that and you don't have a big enough sample size, you're going to be left at the end of the day with something that's completely inconclusive. Precision, if you're doing reliability studies, it's really important to power for that precision, right? I want to make sure my confidence interval is narrow enough that I can say something useful about reliability other than it's 0.01 to 0.99, right? So all of those different goals determine exactly how you do your statistical power. And I think, Keith, some of your next lectures will get into the details of those as I understand the series correctly. All right, I will put in again some resources before we get to the Q&A portion. So again, I have this statistics podcast. We cover a range of fun things, and it's kind of whatever we see in a paper that's fun. I want to point out a new tool that my favorite new statistical tool, which I'm actually talking about in the podcast that's coming out on Monday. So for those of you who are web plot digitizer users, anybody web plot digitizer user? I'm a heavy web plot digitizer user. So if you do systematic reviews or meta-analyses or a lot of statistical sleuthing, statistical review, I use web plot digitizer quite a bit because it's a way to take figures from a paper and put them, you upload them, and then you can actually extract all of the data. Super useful because people don't provide their data sets for the most part still. We don't have a lot of people providing open data. I found a new tool. I was doing this extensive statistical sleuthing for this marathon paper that we're talking about on Monday in the episode. There's a tool called Graph to Table. This is like, going to rock my world because you can take all of the figures in a paper, upload them at once. And unlike web plot digitizer, where you have to click things and you have to be very precise, it automatically extracts all of the data. It extracts the labels, the X and Y labels, axis labels, and puts them and names your variables. So you have ready-made data sets extracted from like 10 figures at once. And it's extremely precise. If you do it multiple times, you get the exact same answers. So it's using AI. So it's my new favorite tool compared to web plot digitizer. And if you do need to use it, I called up the guy who is the creator because I was so happy with this and said, "Hey, can you want to be a partner for the web for the podcast?" So we have a discount code normal curves 20 because it does cost money unlike Web Plot Digitizer, but you can use our discount code and get 20% off. And if you're doing systematic reviews, it is so much easier than Web Plot Digitizer. So I'm going to put my little plug in there for that. I have loads of, I do a lot of training. So I have loads of training resources. So I've written, I haven't really written one in a long time, although technically if I thought of one, I could write another one, but maybe the last one was in 2025. But for a long time, I did a statistical column for PM&R, and I have lots of those columns. Regina Nuzzo, my co-host on the podcast, also had done a bunch of those. So if you want to know about, like, I have one on principal components analysis, instrumental variable analysis, linear regression, multinomial logistic regression. So they're one-off topics. And I try to make them reader friendly. So they're useful if you want to learn about a specific topic. I have a lot of online courses. You can find links to all of those. Just Google me or links through the Normal Curves website. We have a link with all the courses. So I do like medical statistics. Regina and I have kind of a more friendly introduction to data science, and then we do one on clinical trials. And as Keith mentioned, I teach a course on writing, which is actually very popular because scientists don't write well, and this is one of my big pet peeves. We all write badly, and if we could change that, I think it would help science a lot. Like, we do statistics badly. That's my other pet peeve, but my even bigger soapbox, I think, is the way that we write in science, unfortunately, is so hard to parse. And there's just a way to write things that is much cleaner and easier. And I feel like a lot of the scientific nonsense that's going on right now, if we were better communicators as scientists, somehow we could avoid some of that nonsense. So I'll put a little plug in for that course, learning to actually get rid of all the extra jargon and unnecessary wordiness and acronyms, and making yourself clear is really, really important for science, but also important for your career. Because if you write clearer, your papers, I mean, do good statistics, that's central. Do good study design. But if you have two papers where it's like equally good study design, equally good statistics, and one is better written, that better written one is not only going to get published faster, it's going to get much more play. Like, you'll get more citations, people are going to read it because good writing gets read because it's so rare in science. All right, I'm going to stop there.
Awesome. Well, thank you, Kristen. And I think everyone, if you want to join me and give you a real hand, a virtual hand, really appreciate this. And I think that's a great, like, kind of through line in terms of the scientific writing, from just, the statistics comes in with also the clarity of the thinking, right? And then having the clarity of
Yes.
the explanation. So
Yes.
very
It's going to
important.
be really interesting now with AI, of course, because I know a lot of people are using AI for writing. So I have lots of thoughts on that, on the proper ways to use AI for writing. Do not let it write for you. I can tell when it's written for you. Um, but it can be used as a good assistant if you use it right. Yeah. So
Perfect.
yeah, that's a whole other topic of conversation,
Yeah.
but I'm sure it's going to come up a lot with paper writing, study design, statistics too. A lot of that is now being done by AI, so that's a whole other topic we can get
Yeah.
into. Yeah.
Well, and our focus this year is on sample size, but I think there's been a lot of comments on, like, AI in science for maybe focus next year. So maybe,
Yes, I mean,
yeah,
there's yeah, like that. That's a whole interesting topic that I'm thinking a lot about. But yeah, yeah.
perfect. Well, let me go ahead. I'm going to stop our recording.